Welcome. In this video lecture, I am going to talk about how we can perform the explanatory factor analysis using R. So first of all, let's discuss that under what situation we can apply the factor analysis technique. What is the factor analysis and what are its types? Okay, and then because we are going to mainly talking about the explanatory factor analysis, so there is another type which is called as confirmatory factor analysis. But in this particular lecture, we are going to talk about the explanatory factor analysis. So what it is, and then we will take one of the questionnaire which we are going to use in order to perform the explanatory analysis. So first of all, we will check some assumptions, okay, and then we will see the factor extraction methods. So there are multiple factor extraction methods, but we are going to use a PCA method, which is known as a principal component analysis method. And then we will see factor rotation and factor loadings using the different rotation approaches. At the end, we want to get the factor score, which we can use in other techniques such as regression analysis, multivariate analysis, or variance. And then we will see how we can report the factor analysis. So first of all, as we have discussed that under what situation we can apply the factor analysis when we have the variables that are interdependent, which mean we do not know which variable is a dependent, which variable is the independent. So we have the multiple variables and they are interdependence with each other. Okay, so under that situation, and all those variable must be the quantitative variables. So under that situation, we can apply the factor analysis in order to identify the similar sort of variables which are indicating towards a single factor, or you can say a single component. Now the question is, as we are discussing that there are two type of factor analysis. One is known as the explanatory factor analysis, another is known as the confirmatory factor analysis. So first of all, the factor analysis are used to model the observed variable which we can measure directly. Okay, and in an observed variable we check the basically covariance, or you can say correlation structure, in order to get the similar type of variables. However, we can be able to measure the underlying unobserved variable which is known as a latent variable. Like if I can give you the example of, such as we want to check the happiness of the customer, okay, or the satisfaction level of the customer. So we cannot directly measure the happiness of the customer or the satisfaction level of the customer. What we need, we will develop a questionnaire which is basically we are observing directly. So at each, like for example, I have asked 5 or 10 or 8 questions regarding the happiness, and based on those observed variables, we will see whether the customer is happy or not. So basically we are indirectly measuring the happiness of the customer. So all those observed variables, or you can say observed items, used to check the latent variable, or used to measure that latent variable, which is also known as a factor. Okay, now the question is, under what situation we can apply the explanatory factor analysis, under what situation we can apply the explanatory factor analysis. So confirmatory factor analysis we can apply when we have a theory behind it. Like we know the question items of the happiness, like these are the questions which we can use based on the previous literature, that are based on the previous theories, that we can use these items to quantify a variable, latent variable, that is the happiness. Okay, so these are the question items. So when we know this, we can apply the theory driven, which means confirmatory factor analysis, right, in order to confirm whether those variables are measuring those factors. Okay, whereas in explanatory factor analysis, which is basically a data driven methodology, in which we do not know which variable is quantifying which particular factor, or which variable is relating to which factor. So that means we are discovering, based on those observed variable, what factors we can quantify. Okay, mean what those persons are indicating what sort of factor, whether that is indicating the fairness of the customer, or whether it is indicating the happiness of the customer or the dissatisfaction level of the customer. So in this particular lecture, we are going to talk about the explanatory factor analysis, in which we will use a certain questionnaire in order to identify the unobserved latent variables. Okay, mean which variables are relating to factor 1, which variable or which question items are related to factor 2, and so on. Okay, now let's talk about a certain definition which we needed to in order to understand the factor analysis. So the first of all, as we are discussing that what is a factor? A factor is underlying dimension that account for several observed variables. So which means factor is you can say a latent variable which cannot be measured directly, but using certain several observed variable, we can measure that unobserved or the latent variable. So once we have checked that these are the factor which we want to measure, so basically based on those several variables, we try to find out the factor loadings. So what are the factor loadings? That means how closely a particular variable is related to a particular factor. So based on these factor loadings, we will see which 5 or 10 variables are going to indicating the factor 1, which 5 or 6 variables are going to indicating factor 2. So it could be more than or less than variables which are basically indicating that particular factor. So as you can see that basically this is the correlation between that particular factor and the particular variable. So as you have seen from this particular model, okay, or a graphical representation, so we can write down basically if f1 is a factor, so we can say that if this factor is going to be represented with the combination of these three variables, these three observed variables which are relating to this one, so we can write down f1 is equal to y1 plus y2 plus y3, and then there is a errors as well. So error 1 plus error 2 plus error 3 perspective. Okay, but we normally write down not in this linear perspective. Whenever we are writing down, we can write down f1 y1 plus e1, f1 y2 plus e2, and so on. Okay, so that means higher the correlation, better that variable is going to be explained. But we will see later that we want such variables which are not highly correlated and which are even they have the no relationship. So we want the moderate type of correlation, like they have zero point 0.7 or zero point 0.8 near to that one. So we will talk about later this kind of problem. But the most important thing is we want such observed variables which can be correlated with that particular factor. Okay. So the factor loading are basically the correlation between a particular variable and the factor, and it should be the absolute size. So it doesn't have because when we are talking about the correlation, so correlation could be from -1 to +1. So that means the negative correlation is indicating the inverse relationship. But whereas when we are talking about the factor loading, these are the absolute size. They are not depending on any particular size signs. Okay, after that, the most important thing which we are interested in, that is basically the variance in that particular item, whether that variable containing the common variance, which is basically the overlapping variance between the items, as you can see over here. Okay, so whether they have the overlapping or whether they do not have the overlapping. Okay, so once we are the most interested in the overlapping variance, and then every item has a unique error variance as well, that is purely related to that particular variance. So out of that, we are mainly interested in the common variance. Okay, we also calculate the unique variance as well, but the common variance is calculated based on the commonality. Okay, so commonality means that is the common variance for the item. That means how much each variable is accounted for a particular factor. Okay, so that means higher the common variance between the variables, those variables are going to relate to that particular factor. So we can think about this commonality in terms of R square. So that means how much variation that particular variable is going to be explained in that particular factor, okay, in terms of that factor, as I have given in the example over here. Okay, and how we can calculate the communality of a particular variable. So this is the formula for, that is ith factor loading for factor a square and then so on. And lastly, the most important thing is the eigenvalue. Basically, the eigenvalue is indicating the importance of each factor in accounting for the particular set of variables. So higher the eigenvalue, that means that variable is able to explain the more variation in that factor. Okay. So we will see this when we are going to perform in R. So for that, I'm going to use the questionnaire of R anxiety questionnaire. So this question items are this one, which is from 1 to 23. And for this questionnaire, we are quantifying using the Likert scale, okay, where SD is strongly disagree, disagree, neutral, and so on. Okay, and the data is available in this data file. So let me open R and then I will show you the data. So we have 23 questions which we ask related to the anxiety perspective. So we want to measure the anxiety of the R from the students. So let me open this one. So first of all, in order to perform the explanatory factor analysis, we need these three packages. Okay, so first of all, you have to install it. I have already installed. Now I'm just loading these libraries, or you can say packages, and then I'm reading this data file, which is basically .dat, because that is in the data file. So that's why I'm using read.dlt, because this data file is already in the same project where I have put my R code. Okay, this is the data set. So that's why I can read with this function with the read.delim. Okay, and header is equal to true mean the first row is going to be used as the name of the variable. Okay, let's run this one. So this is the data set. So let me see the head of the data set. So these are the 23 questions. This is responded 1, okay, response. This is responded 2's response, and so on. So let's see the tail. So that means there are 2571 respondents, which are basically the students responded. Okay, now the first step we need to do is, that is basically we need to check certain assumptions. So in order to do that, first thing we are going to perform the correlation matrix. So that means we are going to develop a correlation matrix. So let's compute out the correlation matrix first. That is with the help of this command, which is RAQ matrix. In this particular variable, I am going to store the correlation between these 23 variables. Okay, then I am rounding it. Okay, so this is the correlation matrix. So what we need to do is we need to check, there could be the two type of problem as I have mentioned earlier. So we need to check whether the correlation has not enough correlation, okay, or there is a too much correlation. So first of all, let's check the first one, which is basically we can check with the help of Bartlett test. Okay, in order to check is there enough correlation between the variables or not. Okay, so how we can do that? That is, we are going to check our null hypothesis that R matrix, which means the correlation matrix which we have computed, is equal to the identity matrix or not. Okay, so that means the null hypothesis, the R matrix is going to be the identity matrix, whereas alternative is that the correlation matrix is not equal to the identity matrix. So this means if H naught is going to be accepted, that means there is no correlation between the variables. Okay, if H1 is going to be accepted, that means there is a correlation between the variable. So how we can do that? We can check this one through the help of Bartlett test of sphericity. So that is, we can perform through our life with the help of this particular command. So you can apply this Bartlett test of sphericity on a raw data, mean that is the data which we have stored in this raw data, or even you can also apply on the correlation matrix which we have computed this way. Okay, so if you want to apply on the raw data, then the function is cor test.bartlett test, that is the RAQ data, that is basically the name of the variable in which we have stored the data. But if you want to apply this test on a correlation matrix, then you also need to tell the name of the variable in which we have stored the correlation matrix, as well as you need to tell the number of respondents, okay, or you can say the sample size. So you will get the same answers. Okay, so how we can interpret this one? So we can the interpretation would be because the p-value is less than your pre-decided, either it is 1% or 5%. So that means we will say reject h naught. Okay, so the p-value is less than alpha, so we will say reject h naught. That means the R matrix is not equal to the identity matrix, which means there is a correlation between the variable. So whenever there is a correlation between the variable, which is good for the factor analysis, so that means we can say that this problem is solved for this particular data set. So that means there is this problem is not occurring in this data set, that there is a correlation between the variables, so which is appropriate for the factor analysis. Now we need to check the second one, that is there any high correlation over there, like maybe between the variable more than zero point 0.8 or zero point 0.9, that may also create certain problem. So there is a two way to do this. One is that we can check the every correlation items, or another way is we can apply the determinant. We want to find out the determinant of the matrix. So once we have find out the determinant of the matrix, if it is greater than 0.0001, so we will say it's okay. So that means this problem is not occurring over there. So let's find out this one, that is with the help of this command. So as we can see that this value is greater than from this number, so that means correlation is also not too high, okay, which is normally says that more than zero point 0.9 or something like that. So both the problems are not occurring in this particular data set, okay. So there is a enough correlation that which is appropriate for factor analysis, but there is not too much correlation, okay. So that may be possible creating certain problems. Okay, once we have done with this, with the help of correlation, the next thing we need to check the sample size. That is the sample size is appropriate or not. So for that, we are going to apply KMO test. Okay, that is known as measure of sampling adequacy. So that is basically the ratio of squared correlation between variable and squared partial correlation coefficient between variable. And KMO statistics is always lying between 0 and 1. So 0 is indicating that the factor analysis mean near to 0, or you can say exactly equal to 0 mean factor analysis is not appropriate, or you can say the sample size is not enough. Okay. Whereas the KMO is near to 1, the factor analysis is more appropriate for that one. Okay, so as you can see that, so this is basically the reference table for the KMO statistics, which I have taken from the field book, okay, Andy field book. So he says that if the KMO value is above 0.90, that means that is a acceptable level, super acceptable level. If it is like between 0.8 to 0.9, it's great, okay. But usually it is saying that if your KMO value is more than 0.5, it is acceptable. But mostly people are also talking about if it is more than 0.6, that is also acceptable. So that is, you can say that it should be more than at least 0.5. Okay, so but for our data set, first of all, let's see how we can apply this KMO test statistics. That is, we can use this function, which is capital KMO, and then name of the variable in which we have the raw data. So once we have done this, as you can see that this is overall KMO, this is each questionnaire KMO, and how we can interpret that because the overall KMO is more than zero point 0.9, so that means that is highly acceptable, as well as we have to check that every question item's KMO should be greater than 0.5, which is also there. If any of the questionnaire KMO value is not greater than 0.5, so you can think about excluding that particular variable from your analysis. Okay. So as we can see that in terms of initial preparation and analysis perspective, we have applied the correlation matrix in order to check is there enough correlation that is appropriate for the factor analysis, or is there too much correlation or not. Okay, so these two problems must be not present in your data. Okay, so we have checked with the help of Bartlett test of sphericity, as well as we have checked there should be not too much high correlation, that the determinant should be more than this one. If it is there, so that means the correlation is not too much over there. And at the end, we have checked the sample size using the KMO test. So all the assumptions are fulfilled. Now the most important thing is we want to find out of these 23 questions, okay, which set of questions is going to represent factor 1, which set of questions are going to present factor 2, and so on. But what we are going to do is, in an initial analysis, we will say that if we have 23 questions, we have 23 factors, okay, and we are extracting those factors with the help of principal component analysis method. Okay, so there are other methods as well, but right now we are going to use the principal component analysis method. So let's apply the principal component analysis method. So how we can do that? That we can again use the raw data, or either we can use the correlation matrix. Both the commands are fine. So in PC1, that is the name of the variable in which I am going to store the data. So principal, because I want to apply the principal component analysis, that is the name of the function, name of the variable in which we have the data set. How many factors? As I told you earlier, that because right now we are doing nothing in terms of the rotation. So what is this rotation? We'll talk about later. Right now it is none. So there are different type of rotation methods, but right now we are saying that it is none. So that's where, because it is none, we right now saying that the number of factors are as the number of questions are. So after that, we will see how we can reduce this one. So first of all, let's run this. Either you can use this command, or either you can use the correlation matrix. So both will give you the same answer. Okay. So this is basically the answer we are getting. So as you can see that we have at the end h square and u square. So this is the commonality. This is basically unique variance. Okay. So because this entire matrix would be known as the factor loadings. Okay. This is basically the factor loading matrix. And this thing I will talk about later. Right now we are talking about commonality and the common variance, because this commonality is one, because we have considered all the variables as equal to the factor. So that means we extracted 23 factor, which is equal to the number of variables. That's where the commonality is equal to 1. So that means all these factors are able to explain all the variations. Okay, so that's where we can see that the unique variance is equal to 0. So 1 minus this one would be, so all these are zeros. If we are going to pick the lesser number of factors, okay, so that means instead of using 23, we are going to pick this number. Okay, over here, let me tell you over here. Okay, if I write down 22, 21, 20, so this commonality is going to be reduced from 1 to certain number. We will talk about later, but let's first of all understand what does this mean. This SS loading mean. That is basically equal to, in R, this SS means sum of squared of loadings. That is basically the eigenvalue. And what is the eigenvalue? That means how much variation that particular factor is able to explain. So as we can see that this 7.29 is basically factor 1's eigenvalue, or you can say loading, sum of square of loading. So that means 7.29 unit of variance out of 23 number of factors. This much variation is factor 1 is explaining. So in terms of proportion, if we are talking about, that is 7.29 divided by the number of factors. Okay, basically these are the 23 factors, or you can say components. So that means 32% of the variation this particular factor is able to explain. Okay, so the next thing is, which means now we are going to talk about how much factor we need to extract out of these 23. Should we consider all 323, or should we consider first 15 or 10 or 5? So there are certain criteria in order which we can use to extract the number of factors. So one of the criteria is Kaiser's criteria. Another is Jolf's criteria. Okay, so this criteria says if the eigenvalue is greater than 1, that component or that factor is going to be picked. So as you can see that the eigenvalue is greater than 1, this one, this one, this one, this one. So 4 factors having the eigenvalue is greater than 1. So that means out of these 23, we are going to extract, or we are going to pick these 4 factors. Okay. Similarly, we can use Jolf's criteria. He says we should pick all those factors which has the eigenvalue more than 0.7. So according to this, so we can pick first 10. But there is another criteria which we can use, that is basically the Scree plot. Scree plot, that is look like this one. So let me draw first of all, and then we will see how we can interpret this one. So these are basically the eigenvalues. Okay, and let me draw the Scree plot. So how you can interpret it, that we will see that it is look like the elbow. Okay, arm, human elbow. So where this is going to be straightened. So after that we are not we will stop it. So as you can see that we can stop at the point 5. So before this, all the components we can consider as a factor extraction, that is number 1, number 2, number 3, and number 4. So that means according to the Scree plot, it is also saying that we should pick 4 factors. Okay, so that means according to we can say that according to Kaiser's criteria of eigenvalues as well as Scree plot, so we can pick 4 factors or 4 components that would be best for this particular data set. So instead of using 23 factors or 23 components, so we should pick 4 factors. So here are a few tips as well. So it says that if the number of variables are less than 30, then use eigenvalue greater than 1. So that is Kaiser's criteria. Okay, and as long as your communality are overall more than 0.7. But likewise, if your sample size is more than 250, then the average communality 0.6 would be also fine. And alternative, this is that if the sample size is 200 or more, then the Scree plot can be used in order to extract the number of factors. So these are the just steps. So you can either use these mainly criterias. Okay, so these two are mostly widely used criterias. Now let's talk about the rotation. Okay, first of all, till now we haven't used any rotation. As you remember, we talked about earlier that the rotation method we were using none. Okay, but now we are going to apply the rotation. So first of all, what is the rotation? So rotation basically is used to calculate the number of variables that are related to a certain factor, or that are indicating or you can say uh, representing certain factor. Okay, so right now if we rotate certain factors orthogonally, orthogonal means they are totally independent or unrelated. We want certain factors, okay, 1, 2 or 3. So all those factors should be independent from each other. Okay, so that means there is no correlation between them. Okay, so that's why mathematically we can say that they are orthogonal from one from each other, or perpendicular one factor to another factor. So that's why we are, whenever we are going to rotating those factors, so they should be totally independent. Okay, but there are certain areas such as you can say psychology, in which we can say that those factors shouldn't be 100% independent. they may have certain correlation. So if you want such sort of rotation or such sort of relationship between those factors, then we can use oblique rotation. Okay, so that means we want that those factors must have certain correlation. Okay, so basically what the rotation do is it will find out set of variables, or you can say set of questions or set of items which are basically relating to a certain factors. Okay, so higher number of factor loading is indicating all those variables are related to a particular factor, whereas against the other factors, those variables having the lower factor loadings. Okay, so let's apply this one. First of all, I'm going to apply the orthogonal rotation, and in R we can apply in which we are assuming that those factors should be 100% independent from each other. So that means we want to say them that there should be no correlation between those factors. Okay, so when we are rotating orthogonally, so we have four options available in R. Either we can apply Varimax. Okay, so these are the techniques which we can apply when we want to apply the orthogonal rotation. So Varimax are recommended out of these. So whatever the technique you want to apply, you can mention in the rotate is equal to. But right now I'm going to apply the Varimax. How can I do that? So I can run this particular command, that is the same command, okay, which we have used earlier. Okay, but right now let me tell you that as we have extracted the four factors, okay, with the help of Scree Plot. Okay, so principal, raw data, number of factors 4, and the rotation is very max. So let me run this command, and then in order to find out, so this basically the print size. So let me run, and then I will let you know. Okay, so this is how we have extracted. So that means this function is going to indicating which basically variable or which question item is relating to which particular factor. Okay, so how we can interpret this table? So let me show you this one. So basically what this function is doing is it will first of all we are giving the cutting point. So that means we are saying that if the factor loading is zero point 0.3 or less, okay, so that is basically the cut point. Okay, so then we are going to not pick that item for this particular factor. Okay, and then reorder the item and try to put the factor in a sorting option. So this is the most important thing is, so the true mean we should also sort this one, mean higher the factor loading is going to be appear at the top, and then the lower factor loading, then lower factor loading, and so on. So from this question item, which are the 23 questions, as you can see there, these are the 23 question items. Okay, question number 6, 18, 13, 7, 14, 10, and 15. So these question items is basically represented in RC3. That is basically indicating a single factor, which has the higher factor loading. Although these factor also have certain factor loading, but as you can see that question number 12's higher factor loading is 0.52. So this one is smaller. So that means question number 12 is not relating to this particular factor, but question number 12 is relating to this particular factor. Okay, so let's see. First of all, question number 6, 18, 13, 7, 14, 10, and 15. So what they are basically indicating. So question number 6 is basically, I have little experience of computer. Question number 18, are always crash when I try to use it. Question number 13. So basically, I worry that I will cause irreparable damage because of my incompetency with the computers. So if you see all these questions, basically they are indicating towards the fearness of using R as well as using the computer. So that means these questions are basically the combination, or you can say these questions can be labeled as a factor of fear of computers. Okay, or you can say fear of computer and R. Okay, now the second factor, that is basically this one. Basically they have the higher factor loadings. So this is 0.68, 0.66, this is minus 0.57. So why we have the negative factor loading? You can, this is basically due to the negative, mean inverse question. So this positive mean we have the direct question. Okay, this is the inverse question. So if we see question number 20, that is basically I cannot sleep for the thoughts of eigenvector. So this eigenvector is basically mathematical perspective point. Question number 21. I wake up under my debit thinking that I am tapped under a normal distribution. Okay, question number 3. Standard deviation excite me. So this means normally we are asking in a negative perspective. Okay, where we are over here is in terms of anxiety, we are actually asking in terms of the positive. Means that is exciting me. So that means this question is the inverse. So that's where the factor loading is negative. Okay. By the way, if you see these all these questions from question number 20, 21, 3, 12, 4, 16, so they are related to the statistics perspective. So that means we can indicate that it is basically indicating the factor of fear of statistics. Okay, so that is the second factor. So now the third factor basically, that is basically this one. As we can see that question number 8, 17 and 11 are related to the towards the mathematics, and that is indicating the fear of mathematics, which we are labeling as a factor. And lastly we have the peer review. Okay, so that is basically you can say fear of the peer evaluation as a factor, because question number 9 is saying my friends are better at statistics than me, so my peers are better than me. Question number 22 says my friends are better at R than I am. So that is the fear of peers evolution evaluations. Okay, so that is also another factor. So these are the four factors which we have find out, and they says that all these 23 questions are basically representing these four factors. So we can quantify the anxiety of R through these four factors, which are basically the fear of statistics, fear of mathematics, fear of computer, and peer evaluations. Okay, fear of peer evaluation. So let me apply the oblique rotation, because in our study, so all the factors are related to the fear perspective, that is fear of statistics, mathematics. So that is the fear relating. So that's why we want that they shouldn't be 100% independent from each other. They can be correlated, because the fear of one thing can be having the fear of another thing. Okay, so that's why instead of applying the totally independent approach, or you can say that is basically orthogonal rotation, we should apply the oblique rotation. So in R, when the factors are relating with each other, so we are going to apply oblique rotation, and oblique rotation we have different methods. So right now I'm going to use oblimin. Okay, so that is they have the same command, that is basically over here. Okay, so this is the same command in a rotation. Instead of using Varimax, I am using oblimin. So let's run this one again, cutting point and sorting. Okay, the only new thing you will find out when you are going to apply the oblique rotation, you will also find out the correlation matrix. Because in the Varimax, which is basic, the orthogonal rotation, you never find out the correlation matrix, because in over there that is we are saying totally independent. That means that is identity matrix. But over here, because we are saying that the correlation between the factors are possible, those four factors, okay, having certain correlations. So you can see that which factor is having the positive correlation, which factor having the positive correlation, and which factor is having the negative correlation. That is due to because we are allowing those correlation. So let's interpret the results. So from the even when we are rotating the oblique rotation, oblique minimum, so we are getting the same four factors: factor 1, factor 2, factor 3, and factor 4, and which are basically the same four factors. But right now they may have the different order, but they have the same four factors. And lastly, as we have seen the correlation, so this correlation is indicating that these factors are interrelated with each other. Whereas in you can say orthogonal rotation, this correlation matrix is always the identity matrix. That's why R never shows you. Okay, at the end, what we are going to do is we are going to get the score. Okay, that means that is known as a factor score. So basically, this factor score that is basically indicating how much score we are going to give this one, this one, this one, and this one. Okay, so these are basically the four new variables you can say that which basically we can use for the further analysis in terms of we want to find perform certain regression analysis, MANOVA or ANOVA or a cluster analysis. So how we can find out the factor score against these four factors? So with the help of this particular command. Okay, so let me run this one. Okay, that is basically this one. Only the addition is that is basically the score is equal to true. So if I run this one and then I can use PC5 $ to find out the get the score. Okay, let me see to get the scores. Okay, so if I run this one, so I am getting the score of those four factors. Okay, that is basically this one. So this is factor 1 score, factor 2, factor 3, factor 4, and using this particular command I am combining my raw data as well as the factor score. Okay, so that would be basically look like this one. So till over here we have the, okay, let me show you. Okay, so till the end, we have basically the four new variables. That is basically the factor score. And the remaining 23 is basically the actual data set. Okay, so I hope you got the idea how we can perform the exploratory factor analysis in R, as well as how we can get the factor analysis factors from the questions. So now the question is how we can report it. This is the way we can report it. That is basically according to the orthogonal, which means Varimax rotated factor loadings. So we are writing down every question items. Against that, we are mentioning the factor loading. So the bold color is basically indicating that this question item is indicating this particular factor. This question item is indicating this question. So that means this factor is going to be measured using these 6 or 7 questions. Okay, similarly we can see that fear of statistics perspective, peer evaluation. Okay, then fear of mathematics, we are going to measure of this using these questions. We are mentioning the eigenvalues, or you can say the sum of square of loadings, percentage of variation, how much variation that particular factor is going to be explained. And then at the end we are mentioning Cronbach alpha. That means this factor having how much Cronbach alpha. So how we can calculate that one? So right now over here the factor loading, that is the cut point we have used, that is zero point 0.4. So it's up to you which you want to use, 0.4 or 0.3. Normally people are using 0.3 or 0.4. But let's find out the reliability analysis, or you can say the Cronbach alpha. So first of all, I am creating a variable computer fear in which I am mentioning out of my data set, which is RAQ data, that is the variable in which we have stored the data. I am selecting 6, 7, mean these are basically the question items. So every column is basically representing a question item. That is question number 6, question number 7, up to question number 18. Okay, 6, 7, 10, 13, 14, 15, 18. These are basically representing a factor called as the computer sphere. Similarly, we have sorted out the statistics sphere, mathematics spheres, and peer evolution. Okay, evaluation. Okay, now first of all, I'm going to calculate basically the Cronbach alpha for the computer fear factor. Okay, so the function is called alpha. So if I run this one and CF and this one, as you can see that, so this is basically the value of Cronbach alpha which we are going to report it. Okay, the raw alpha which is zero point 0.8, which is more than zero point 0.7, so that means reliability value is over there. So this factor is a reliable. So if the Cronbach alpha is more than zero point 0.7, so that factor is a reliable factor. Okay, so you can also extract using dollar sign total. So the exact that number basically this one. So this is also indicating related questions Cronbach alpha value. Okay. Similarly, we are calculating the Cronbach alpha of statistics. So as you can see that if you remember, all the factors questions were you can say on a one direction, whereas when we were talking about the statistics perspective, one of the question was inverse of the questions we were asking in terms of measuring the anxiety. That is basically this one. If you remember this one, that is the question number 3, which is standard deviation excite me. Okay, that is not basically indicating the anxiety, that is indicating the happiness. So basically that is the inverse. So that's why whenever you have the inverse question, so over there, so in alpha function we have called as a key component or a key object in which you can mention that question item. So in statistics, question number 3 was the inverse of all this one. So that's why the key would be -1 against that question. All are one positive one, whereas this one is indicating. So this is the negative or the inverse of these questions. So we have finding the Cronbach alpha of statistics where we have 0.82. Similarly, all have the same similar type of questions. So as you can see, you see that all three variables, that is basically all three factors, computer sphere, statistics sphere, mathematics sphere, they have the Cronbach alpha is more than zero point 0.7, whereas the last factor has the Cronbach alpha which is 0.57, which is less reliable factor. Okay, whereas all three are the reliable factor. So I hope you got the idea that how we can perform the exploratory factor analysis using R, how we can interpret it. So thank you so much. See you in the next video.